Hello students, welcome to your favorite knowledge planet powered by PW. I am Tanya. Yes, I teach physics and today I have the ultimate recap of your chapter Force and Laws of Motion. So in class 9th, this is the second chapter, right? Of course over here we are going to talk about laws of motion. As this is a recap, I will give you the gist of all the topics that is there. Moreover, I'll try to convey the information in a very easy and understandable manner. So, yes, you should have paper and pencil next to you so that you can make your own notes and certainly you can see the things in a different perspective. So, everyone, let's start with the recap and let's start with this ultimate recap. So, take out a paper and pencil and let's start with the first basic thing. So everyone, in this chapter, although we are pretty much into laws of motion and Newton's laws of motion, but before Newton, if I say, there were some people, there were some scientists, there were some philosophers, they actually stated something. So they gave some statements regarding force. So what happened? Aristotle, yes, he gave the first fallacy. Why fallacy? Because yes, whatever statement he stated, that was not true. So, have a look. An external force is required to keep a body in uniform motion. He stated that we require some external force so that the body is remaining in a uniform motion. Now, externally, we need to require, we need to act a force on a body so that it is in uniform motion. Right? Now, after Aristotle, he developed the idea and he said that okay, the idea of force is nothing but as a cause of motion. Right? So, he was very close by, although he skipped on some of the points that Newton specified, but he stated that okay, force is a cause for motion. Yeah, and determine that the natural state, see, natural state of an object is either rest or motion. Either the object will be at rest or uniform motion. Certainly these are the nothing but natural states. Okay, moreover, Aristotle, he only said that okay, an external force is required to keep an object in uniform motion. Yeah, you get the difference between the two? Right? So Galileo and Aristotle, they were the scientist, or Aristotle, a philosopher, he stated something about force. Now as the time passed, so yes, this is a long time back, right? So as the time passed, of course, Newton stated the three laws of motion and he explained motion in a different manner. Although from junior classes we are aware that force is nothing but a push or pull, right? We say force. Whenever we hear this term force, right, two terms, right, they actually pop into our head. What are they? Push or pull. Yeah, but now you will get the understanding that okay, if we are going to use this term push and pull, no, altogether, just like okay, force is a push and pull. No, this is not the proper meaning. Although we have different definitions of force, yet the standard word that we are going to understand, that we are going to see. Okay, so without wasting any more time for the basics and the history as such, let's jump on to the topic that is nothing but force. So all of you, let us take one example and then understand force. Okay, there is a box. I am pushing the box. What pushing? Applying force. Okay, I am applying force on the box. Box is not moving. Okay, you are waiting. After 1 hour you will say, come on, what you are doing? Let me come and let me show you that how force is applied. So I am like, okay, you come. Now the moment you are coming, you are applying the force and the box started to move. So in that case, you are going to say, ma'am, you are not applying force and you are not applying force. See, this is how force is applied. See, this is how force takes place. And see, this is how force is there. So I am telling you, no, I was applying force, but you will tell me I was not able to see the effect. Yeah. So over there, I was applying the force, box not moving. You applied the force, box started to move. So you are going to say, I am applying force, you are not applying force. Why so? Because yes, the effect arose when you started to push the box. Similar way, we open the bottle, right? We try to open the bottle that is pretty much, closed. So when you are trying to apply the force, bottle is not opening, you will say, you are applying force. Certainly you will say you are applying force, but somebody out there and watching you, observing you, they will tell you, no, you're not applying force. And the moment you are going to give the bottle to your parents, right, and they are going to open the bottle, over there as the effect is there, of course, you are going to state, and you are also going to say that, okay, force is applied. Yeah, so over here, one thing is very, very important. When effect is seen, when effect arises, we certainly become more confident when we talk about force. Okay, so force is nothing but a cause that will lead to effect, or let us be more specific, that will lead to, or that will change the state of rest or motion. Right? So now we can say, okay, see, push and pull. All right, yes, force a push or a pull, that will cause the change in its velocity. I'll talk about that. Or you can certainly say change in the state from rest to motion or from motion to rest. Okay, so now you have to write down the statement like this. Push and pull, these two words. No, these two terms, right, they're just giving you some sort of a hint onto that. Yeah, but to talk about force, you have to state force is a push or pull that will cause the change of state from rest to motion or motion to rest. Simple push and push you will not write. Okay, now one term written over here, external agent. Why external agent? Why force external agent over here? See, when you are sitting inside the box and you will try to push the box won't move. Yeah, so yes, force need to be external. You will say, no ma'am, I'm sitting inside the box, I will push the box. But yes, that effect is not that much visible. When you are going to apply the force externally, that is why external agent over here. Okay, now we say force, right? And yes, force is a physical quantity. Let me specify, force is a vector quantity. What do you mean by vector? Everyone, chapter 1. Vector quantity means magnitude with direction. For force, both direction and magnitude, they are important. Without direction, if you're talking about force, yes, half information. Certainly, you are not going to talk about force at all. So, direction is important. That is why force is a vector quantity. As I am saying quantity, there will be a unit. What is the SI unit, everyone? SI unit, System of International Unit, the unit that we are using for all the experiment, for all the observation. What is it? It is nothing but Newton. Okay, now whenever we talk about SI unit, we always talk about CGS units, kids. Okay, so if I say I am measuring the length of a pencil, and certainly the SI unit will be meter. CGS unit, smaller unit, or let me say centimeter, gram. Second unit will be nothing but dyne, D-Y-N-E, D-Y-N is the symbol. Okay, symbols are very, very important. Without symbols, right, certainly half information you are stating. Okay, try to use symbols. So if I say 4 Newton with the arrow, this is the proper representation of force. Okay, tiny arrow, vector quantity, certain direction, Newton, yeah, number there, magnitude and unit and direction. Okay, so this is nothing but the basic, we are pretty much aware of it. Okay, now I am telling you force is nothing, force is an external agent or a cause. Force is a cause that will lead to effect, yeah, change of state from rest to motion or motion to rest. Certainly over here one thing is pretty much obvious, that yes, when we are talking about force, no, okay, there will be some effects. Okay, so now let us talk about some effects. Let us take one example only and we are going to talk about these effects. Okay, before that, everyone, as I told you that, okay, have a look. Okay, I want all of you to mention this in the chat. Right, everyone, do this thing, right, mention the answer there in the chat. So all of you, 1 meter is 100 centimeter. Agreed? Okay, you will tell me 1 Newton is how much dyne? Okay, right? Very simple scenario. So 1 Newton, you will tell me how much dyne. Mention this in the chat. Okay, now everyone, let's move ahead. I will take one example. I know everyone loves football. Yeah, you all love cricket and football. Yeah, these two sports certainly we all enjoy. Okay, so let's take up the example of cricket. Okay, or you can take up the example of football also. Yeah, so by just playing, we are going to talk about some effects of force. Okay, so there is this game happening. I'm there in the opposite team. You're there in the opposite team, right, everyone? So what is happening over here? Of course, I'm just starting the game. Yeah, so initially when we are starting the game, of course, the ball is in the hand of the player. Yeah, so ball is, so you can say, okay, player is also standing, right? Ball is at rest. Yeah, now when player will throw the ball, what will happen? The ball is going to move from rest to motion. Okay, similar manner if football is there, of course what will happen? Yes, in football as well, initially the ball is there in the center. Yeah, the player will come and kick the ball. So yes, over there, the first effect, rest to motion, can I say? Yeah. First effect. So yes, by applying force, everyone, what is happening? By applying force, what is happening? The body from rest to motion, it is moving. Okay, now you can say, okay, let's talk about football only or cricket, any of it. Yeah, the player is kicking the ball. Ball was moving. He is kicking the ball and the goalkeeper is going to catch the ball. So everyone as a goalkeeper is going to catch the ball. What is happening over there? From motion to rest. So what is happening? When the force is applied, yes, body can move from motion to rest. Also change of state, you can see. Yeah, force is the cause that is leading to the effect. Okay, so yes, this is happening because of cause of force. Yeah, now let's talk about speed. Okay, now I am dribbling the ball easily. Okay, happy. Suddenly another player will come towards me. What I will do? I will kick the ball faster. Yeah, so initially the ball was there in a particular speed. Now I am applying the force and certainly there is increase in the speed. So what I can say? Yes, force can increase the speed or decrease the speed. Okay, yeah, fourth one. Let's talk about direction. So of course, yeah, if I am playing, right, and of course a person is coming towards me, I can kick the ball to the right, to the left, to my friend, to my, another friend. Certainly over there, what is happening? I am applying the force and the body is changing its direction. So force can lead to change in the direction. Yeah, now the last one over here. Yes, force lead to change in the shape and size of the object. Of course, we have heard that. Right? So what is happening when my mother is there or any other person is there, yeah, they are making chapatis. What happens over there? Of course, there's a ball of dough and you are going to press it. By pressing, applying the force, and when you are going to apply the force, there will be a change in the shape. Okay? So these are the effects that we encounter. Right? Now in the definition it is telling us that okay, force is an external agent causing the change in the state of rest to motion. Okay? Or there was one more thing, that change in the velocity. So everyone, when we talk about velocity, right? So we say that okay, velocity will arise when we are saying that okay, change in velocity, right? Certainly if I say okay, change in velocity is nothing on a particular time. If I say it is nothing but acceleration, you remember? Yeah, delta V. Initially the body was at rest, now having some velocity, change in the velocity taking place. That is, in simple terms, that is nothing but acceleration. Yeah, so you can simply say that, okay, ma'am, over here some amount of acceleration we can encounter. Okay, so change in velocity, we mean by that. Yeah, change in velocity by time. So if I say this is change in velocity, delta V, I believe, change. Yeah, and if I say change in velocity, the rate of change in velocity, that will be acceleration. Okay, I am saying rate of change of velocity, kids. So over there we had a word that, okay, how quickly the change is taking place. Okay, yes, from 0 to 100, of course, from 20 to 100, yeah, from 0 to 10, the quickly the change will take place, that matters. More acceleration, remember that part. Okay, certainly this concept should be clear. Okay, now as we are through with the effects of force, certainly we are going to talk about balance and unbalanced forces. Okay, so balance forces, see, all of you tend to get confused that, ma'am, okay, this is nothing but a type of force that we usually talk about. See, when you talk about balance forces, no, yeah, you are concerned with the resultant force. Okay, new term, a resultant force. So all of you, I am saying something. Yeah, and nobody will pause the video or do like that, right? Whatever I am saying, you just have to keep the things in your head and try to call it all loud. Okay, and certainly the things will be clear. See, I am having a bag of 100 toffees. Okay, I am giving 5 to Ram, I am taking 6 from Ram, I am giving 7 to Sita, I am taking 8 from Sita, I am giving 8 to Raju, I am taking 9 from Raju, I am giving 16 to Akshata, I am taking 18 from Renu, I am taking 17 from Prashant. Certainly these are the names I am taking. Okay, now eventually how many toffees are left with me? First of all, do you remember what did I just say? No, right? I also don't remember that what did I just say. So in that scenario, when I asked you that, okay, how much is remaining and how much I am left with, over there you will certainly say, ma'am, we have to do some calculations over there because you are talking about the net, the resultant, the remaining. Similar way on our objects, ample of forces act, and when ample of forces act, we say that, okay, over there lot and lot of forces are taking place. Now, in order to find whether the object will move or whether the object will not move, what we have to do? We have to talk about the net force or resultant force. Okay, resultant force is nothing but the force that usually acts when lot and lot of forces are acting. So everyone, when we say the resultant of all the forces acting on a body tends to be 0. Yeah, so let me say F net is 0. So what you are going to say that yes, the forces are balanced in nature, they are balanced out. Okay, now have a look over here. Let me explain the whole scenario. Balanced forces, they do not change the state of rest or motion. Everyone, let me give you a simple example over here. Okay, now let me say that, okay, you are there. Okay, and it's a Sunday morning. Yeah, you are sleeping. Suddenly your mother will come and she will tell you, wake up. Right? Yeah, get up from your bed. Now, your father will come and he will tell you, okay, no sleep. Right? So, mother is telling you wake up, father is telling you sleep. So, in that scenario, if both of them, they are applying equal amount of force in telling you that, okay, wake up, or no, sleep. So, in that case, what will happen? You will say, okay, I'm not doing anything right now, right? I'll sleep. You guys decide, then I'll do that. Yeah, in that particular case, that will happen. Okay, similar way over here also, when the forces are balanced out in nature, so yes, there won't be any change in the state of rest or motion. Okay, moreover, I'll give the example also over here. Moreover, here one point is very, very important. Balance forces may change the shape and size of an object. So all of you, yes, if there is change in the shape taking place, see everyone, when you are pressing the toothpaste, right, you are applying the equal amount of force on both the sides. Yeah, so over there, yes, balance forces are acting and they may change the shape or size of an object. Okay, now this case only if I take, and let me show you that how the things will come. There is a box. Yeah, on this box, two forces are acting, F1 and F2. and I am asking you find the resultant force. Now kids, this is like the basic. When two forces are acting in the same direction, we always add them. So what you are going to say? The net force on this box is nothing but 5 Newton. Okay, I am giving you the basic. Yeah, then we are going to move ahead. And yes, questions like this only occur. Right? Now, when, see, same direction, add. Now force can act in the opposite direction also. If forces are acting in the opposite direction, then what will happen? You are going to subtract. So F net over here will be, which one is more, 3 Newton or 2 Newton? 3 Newton is more, right? So you are going to subtract F2 from F1, bigger to smaller. Yeah? So you are going to get the answer as 1 Newton. So your F net will be 1 Newton. Opposite, you are going to subtract. Basic, okay? Basic. Yeah, this is the base. Okay, now you can certainly note this down, right? And when we are dealing with any case, of course, over there, not only two forces, ample of forces will act. Okay, so I'll show you a numerical and I'll show you a question. Of course, we are going to practice it all together. Okay, everyone, I believe the things are noted, right? Okay, so let's talk about balance force. So when we talk about balance force, right, we say net, F net will be 0. F net tend to be 0. Okay, have a look. Okay, F1 is 5 Newton, F2 is 10 Newton, F3 is 15 Newton. Now the question will be find the resultant force. Okay, so what you are going to do, first of all, three forces are here. Yeah, if I will increase the number, right, have a look. If I will increase the number, no? Right, so many, 5 forces are here. So first of all, our basic tells us that, okay, whenever the forces are there in the same direction, we will add them. So forces in the same direction, they need to be added. Yeah, so add 5, 5, 10. What you are going to get? 20 Newton. Okay? Forces in the same direction, add. Okay? Now, when the forces are in the, I want F net, I want the resultant. I'm not concerned with any of the amount of forces. Yeah, now forces are in the opposite direction. As forces are in the opposite direction, what I will do, of course, I will subtract them. Okay, 20 minus 20, 0 Newton. Your F net is nothing but 0 Newton. Yeah, as F net is 0 Newton, what you are going to say? Yes, the forces are balanced in nature. They are balanced in nature. They are not going to affect the rest body or the motion body. They are not going to change them from rest to motion. Okay, so over there, you are not going to say that, ma'am, force is not applied. Force is applied. The effect is not seen from rest to motion or motion to rest. Okay, they are balanced out in nature. Yeah, pretty much easy, right? How the forces are balanced. Okay, and the balance means resultant 0. If resultant 0, acceleration is there, no, right? Change in velocity, no, right? So, see, if I am telling you F net is 0, yeah, acceleration turns out to be 0, yeah. How can acceleration be 0, everyone? How can acceleration be 0? Acceleration can be 0 if my initial velocity is 0, final velocity is 0. Everyone, initial velocity 0, final velocity 0, body at rest, right? Yeah, no velocity, no. Similarly, this is the base, huh? Similarly, if initial velocity is 2, final velocity is 2, no change occurring in the velocity uniform motion. So all of you, yes, if the object is at rest, balance forces are applying. Yes, balance forces are applied over there. F net 0, so yes, body won't move. If initially the body was at motion, yeah, and the forces are acting on the body, right? Forces are acting on the body, they are balanced in nature, they are not going to affect its motion because the forces are balanced out. Getting me, everyone? See, object at rest, be at rest, right, when the forces are balanced in nature. Okay, similarly, initially the body had some motion, right, and when you applied forces, and yes, forces are acting onto it, right, and they are balanced in nature, they are not going to affect its motion, right, because they are balanced forces, their F net is 0. Okay, everyone, right? Now, moving ahead, one thing is balance, other one will be unbalanced, right? Yeah. So, in unbalanced scenario, what will happen? F net will have a value. You can say F net will not be 0. As F net will not be 0, of course, there will be some velocity. Of course, there will be some change. Of course, there will be some acceleration. Okay, if you're getting confused with the term acceleration, right, just take up this word, effect will be there, that's it. Keep effect will be there with us, that's only the thing that matters. Okay, don't go ahead in acceleration if you're not comfortable, but I would suggest that please have a look on the first chapter, over there acceleration, everything also, yeah, because that will clear your concept. Okay, so come back over here. Unbalanced forces, resultant of the forces acting on a body is not 0. As it is not 0, F net will have a value. F net will have a value. Certainly, the object will move. There will be some change taking place. Okay, so what type of change will take place? Yes, it will produce the change in its state of rest or uniform motion. Okay, how? Let's see, no. Yeah. Okay, now ample of forces are there. Okay, easy. Now initially you try. Okay, now you try, you tell me the answer in the chat. I would love to see. Yeah, try, give it a try. Easy, very easy. Right? In this case, first we know forces in the same direction, they are to be added. 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 Right? So if I draw force from the right, 5, 4. 5, 4, 9. Okay, forces from the left and right, right will be 12, 5. 9 and 17, opposite direction subtract, okay? 17 minus 9. Yeah, so F net will be 8 Newton, yes or no? Yeah, 8 Newton, right? So in this particular case, there is some value in the F net, so you can say, ma'am, yes, the body is going to move. There will be some change taking place, there will be some effect we can encounter. Okay, so this is how the scenario is there. Unbalanced case, forces are unbalanced in nature. What they will lead to change in effect, that's it. They will lead to effect. They will lead to change in the rest to motion or motion to rest. Okay, now as we are through with the unbalanced forces, yes, we are going to understand about something called as inertia. So lot of kids, they get confused that okay, inertia is something, right? Kids, inertia is a property. Yeah, to resist itself. See, if I tell you that, okay, yeah, it's a Sunday, right? Every day Sunday, certainly Sunday we say, okay, it's a Sunday, yeah, and your mother is coming and telling you to wake up, you will tell, no, I don't want to wake up. No, I don't. Yeah. So over there you are resisting yourself, no? So inertia also does the same. Inertia is a property. Okay, if anything is there at its position, the body wants to be there at its position only. Body at rest, want to remain at rest, don't want to change. Yeah, so we generally say, no, changes are good for nature, but yes, if anybody is not that much adaptable to change, right, so we are going to say, okay, yeah, probably, right, having some issue. So inertia is a property of a matter by which it remains at the state of rest or in uniform motion. Yeah, moreover, if it is there, no, so yes, if it is there in the motion, it wants to be there in that straight line. Everyone, yeah, nobody likes to move in circles. Yeah, if a body is having some amount of feeling or certain something like that, no, so your body will tell us that, okay, I don't want to go in the circle, right? So they always want to move in the straight direction, move ahead. Okay, similar thing happens in uniform motion also. It wants to remain in the same straight line unless we don't look on this unless ultimate upon some external forces acting. Okay, don't look on that. Yeah. So when we talk about inertia, certainly inertia is nothing but the property of matter. Okay. Moreover, when you use this term, right, inertia, you should think of this term that, okay, resistive in nature, doesn't like to change. Yeah, like that. Okay, so if you are there sleeping, yeah, or let me give you one more example, yeah, you are playing outside, your mother is calling you, come inside, right? You are going to say, no, I will play 5 more minutes, 10 more minutes. You are going to resist that thing, right? Over there, yeah, inertia. Okay, want to play, continue to play, don't want to go home. Yeah, want to go out, stay out, don't want to come home, like that. Okay, so that type of property you can certainly say. Yeah. Now, when we talk about inertia, as it is a property, everyone, right? I am talking about inertia because yes, the first law talks about inertia only. Okay, so when I am talking about inertia, you should be clear that, okay, over here, we as a human being, or we as bodies, right? Certainly we say that, okay, there are 3 basic scenarios that we encounter: inertia of rest, motion, and direction. Okay, so when I am talking about inertia at body at rest, let us take one example over here. Okay, so let's say that, okay, you are traveling in the car. Yeah, when you are traveling there in the car, of course, or one more easy example, right? Glass. Okay, glass, keep a card and a coin. Okay, I believe you all have seen this example in the book also. Right, so what will happen when you are going to flicker, when you are going to apply force on the card is going to move away and the coin will drop down. Okay, so why the coin is not moving that much far away? Coin is saying, okay, I am at rest. Yeah, force is applied on me. No, right, force is not applied on to me, no, so why should I change? Getting everyone, right? So the coin was at rest. Yeah, you are not applying the force on the coin, you are applying the force on the card. So over there, coin will say, you are applying force on me. No, right? So why should I change? I don't want to change. Yeah, so over here, the coin is going to drop down. Okay, similar way, when you see those leaves and apples or any fruits right there onto the branches of the tree, what will happen? You are applying force on the trunk of the tree or probably the branch. Yeah, leaf is there intertwined. Okay, so leaf will say, I am at rest, no? Yeah, you are not applying force onto me, right? Okay, so why should I change? I will be there, right? Although because of that, because the resistive property of the leaf, right? So yes, it is going to fall down there onto the ground, but you are not applying force on the fruit itself, the leaf itself. Okay, so it will be there in the property of inertia only that, okay, it is going to resist. I am at rest, no, I want to remain at rest, right? Okay, similar way, motion. Yeah, now I will take up the example of that. All of you give me one example of inertia, type of inertia at rest there in the chat. Okay, by that I will also get the understanding that you get it. Any example. Okay, now inertia at motion. So everyone, when we talk about motion, right, you are traveling in the car. Okay, uh, very enjoying your pace and everything is there. So suddenly the brakes are applied. So what will happen as suddenly the brakes are applied? Of course, you were there, right? So you feel that the body is not working with you. Why so? Have a look. When we were moving and suddenly the brakes are applied, so what happens? Our body wants to remain in motion. Yeah, although the force has been acting onto it and certainly you have to stop, but the body won't work with you. Why? Because yes, your feet is there, no, onto the car floor. Yeah, so over there it was moving, and as it was moving, it wanted to be in motion. Okay, similar thing happens when you were there at rest, the car will start. So what will happen? You will go back. Why this is happening? As the car is starting, my body was there, no, at rest, right? My body, the upper body, right, will say, okay, I want to be at rest only. Okay, clear with it? Yeah, there are ample of examples are there where we actually see the types of inertia and we encounter them also. Okay, now direction, this thing is very important, right? Why so? See, when we say that okay, you are there on a hilly road, or when you are there in the traffic and you want to dodge people out, right? So what the car will do? Go left, right, left, right. Yeah, and over there you tend to see, right, and you tend to experience, so your body dangling. Yeah, as your body is dangling. Why so? Because yes, when we were there in a particular direction, my body tends to wants to and tends to remain in that. Yeah, when you're going to move when you're going to move the vehicle, no, in the opposite direction, right, the body wants to remain in the initial position only. That is why we feel that dangly thing happening. Okay, moreover, in all these scenarios, as we talk that okay, types of inertia is taking place of motion, direction, and rest, and we encounter these scenarios in our day to day lives as well. Of course, I want you to go and explore onto it. As this much inertia property, we are going to take and dump it onto Newton's first law of motion. So, everyone, have a look. You will see similarity. A body at rest will remain at rest. Okay, and a body in motion will continue in motion in a straight line with uniform speed until and unless it is compelled by an external force. So all of you, it is advisable that you are stating the definitions, the laws in the proper statement that is given in the book. Okay, you should not use any of the other your language for it. Yeah, because yes, as it is stated by someone, no, so yes, you should be using the same language. Okay, so over here what is happening? Everyone, see, let's take one example. Sunday morning. Yeah, Sunday morning, you are sleeping, mother will come, wake up, father will come, sleep. Now in this particular case, when both of them, they were balanced out, so yeah, nothing was happening to you, you were sleeping. But if I will tell you in this case only, your mother will tell you, wake up, yeah, or else you will see, right, or wake up or you're not going to get your breakfast. So in that particular case, right, what is happening? Yes, your mother is becoming more, applying more force over there, and the situation is becoming unbalanced. As the situation is becoming unbalanced, what will happen? You are going to move, wake up and go and have your breakfast. Yeah, so in that case, what happened? Initially, the situation was balanced out, but when your mother applied more force, the situation turned out to be unbalanced. Yeah, and when external forces acting, or you can say the situation is becoming unbalanced over there, what will happen? There will be change of its state or uniform motion. Okay, other words, easy words, right? Inertia of a body can only be changed when force is applied. So you can change the inertia, you can change the state of rest, you can change the state of uniform motion when an external force will be applied. Okay, see what is happening when you are going, no, your father is also going, right? You are there on the bike or scooter or a car. Yeah, Yes, if your speed is remaining same, everything is there, no forces are balanced in nature, that okay, yeah, same speed, acceleration 0, see, 40 meter per second, 40 meter per second, acceleration 0. As acceleration 0, what you are going to say that yes, the force net, F net will be 0, balance out scenario. Yeah, I'm taking out the balance out scenario, 4 0. Okay, so over there everything is balanced out. Yeah, but suddenly when he is going to apply, like accelerate, yeah, or he is going to apply the brake, of course what will happen, you are going to see the effect rising. Yeah, you can see that, okay, moving forward, backward, yeah, sudden movement taking place, sudden change, right? Why this is happening? This is happening because of Newton's first law, right? So he is saying that when the force is applied on that scenario, of course there will be a change of state. Okay, until and unless you are not applying any external force onto that balance scenario, a body at rest will remain at rest. Okay, and yes, over there the force will be unbalanced in nature. Only unbalanced forces will lead to effect, as we saw. Okay, as the body was in motion, continue in motion, rest at rest. Everyone clear with it? Okay, so Newton's first law states that, okay, when inertia of a body, yeah, you want to change the inertia of a body, force has to be applied. Okay, in order to change the inertia of a body, force has to be applied. Right? Pretty much easy scenario. Right? As we had a word on Newton's first law of motion, we also say this thing, right? That okay, it will actually tell us a body, whatever state of the body is there, it should remain in that state. Okay, so in easy terms, if you want to understand, so you can say, okay, no change taking place, a body resisting the change. Like that you can understand. Okay, now moving ahead, we are going to talk about something called as momentum. So when you talk about momentum, you have to be sure that yes, it is nothing but defined as a quantity of motion. Okay, as a body is there, and you want to talk about the quantity, right? Quantitative purposes, right? So quantity of a motion contained in a body. How much motion contained? That your momentum will tell you. For momentum, yes, the symbol turns out to be P, and in order to find momentum, you require mass and velocity. The product of mass and the velocity of the body. Okay, so momentum is nothing but the quantity, how much motion is there in the body, how much quantitative motion will be there in the body, that will be given to us by momentum. Okay, small p is the symbol. Now, product of mass and velocity. Yeah, so product of mass and velocity, if I am telling you, so of course, what is the SI unit of mass? kg. What is the SI unit of velocity? Meter per second. So the SI unit of your momentum will be kg meter per second. Okay, directly in the formula I am placing. Yeah, SI unit of momentum. Okay, now in this case, if I tell you, so of course velocity is there, certainly you can say, ma'am, momentum will be a vector quantity, direction is important. Right? All of you, momentum, have a look. Momentum is nothing but mass into velocity, the quantity of the motion, quantity of a motion contained in a body. Right? Now, if you want to change the momentum, or sudden change is rising in the momentum, yeah, how that will occur? Moreover, what are the factors on which momentum will depend upon? So one by one, let's see both the cases. So, factors on which momentum will depend upon. Okay, have a look. Momentum is mass into velocity. So in simple terms, you can say either mass or velocity. Right? So let's talk about both of them. Have a look. Whenever you talk about momentum, kids, remember mass of the body matters a lot. Right? And velocity of the body matters a lot. Yeah? More the mass, more the momentum. Right? More the quantity. Okay? More, see, if I will tell you, go stand in front of a truck. A truck is coming out to be in the speed of 20 km per hour. You will say, no, ma'am, more, mass is pretty much high, right? More momentum, more hurt I will get. Understand momentum with hurt. How much hurt you are going to get. Yeah, if I will tell you go and stand in front of a boy running in the speed of 20 km per hour, you'll say, okay, still I can go and try to stand over there. Yeah, so understand momentum as the hurt. How much hurt you are going to get. More the mass, of course, more the speed. Have a look over here. So when I say that, okay, there is a truck. Okay, mass is 1000 kg. And there is a cycle. Mass is, let's say, 50 kg. Both are coming with the velocity of 10 kilometer per hour. Right? So in this particular case, if I will tell you, or let's say 10 meter per second, you will say, no ma'am, kilometer per hour. Why I change, everyone? Why I change this kilometer per hour to meter per second? Because the standard unit says so. Okay, kg, meter per second. So if in the question also you have to change. Yeah, remember this thing. Okay, kilometer per hour needs to be changed to meter per second. Else you are not talking about SI unit, and we work with SI unit. Okay, so over here if I will tell you, velocity is same, mass is more. So simply don't solve it also, right? Yeah, just simply by looking, can you say something? What? Ma'am, more the mass, more will be the momentum. More quantity of motion contained in the body. Right? Similarly, ma'am, mass less, momentum will be less. Okay, this is how. Yeah, similar way if I will tell you that, okay, over here both cycles are there, cycle 1, cycle 2, both have 10 kg mass. Okay, but one is moving with the velocity of 50 meter per second, other is moving with the velocity of 200 meter per second. So over here, can you see? Yeah, two bodies are having same masses. Over here, who is the counterpart? Velocity. Okay. Yeah, pretty much easy, right? Yes, numericals like this only will come. Alright, you just have to analyze it. Now, as I am telling you, momentum will talk about the quantity. Newton's second law is also the quantitative law. It will tell you how much quantity of force is there. Okay, so Newton's second law, when we talk about, of course, it will tell us that yes, the quantity. Okay, quantitative law. We talked about that, okay, until unless force is applied, no change. Yeah, over here we'll be talking about the quantity. Yeah, so have a look. Over here, what is it in? The rate of change of momentum of a body is directly proportional to the force applied. What they are telling us? They are telling us that, okay, momentum, everyone, momentum, change of momentum. Change of momentum will be initially momentum, final momentum minus initial momentum, no? Yeah, let me show you. Mass of a body moving with velocity, mass of the body, same. Okay, moving with some other velocity. Okay, change in the momentum. Right, so over here if I will tell you, mu is the initial momentum, mv is the final momentum. If I will talk about the change in the momentum, you will say final minus initial, change in the momentum. Yeah, so change in the momentum of a body. Here, don't miss out the term rate. So I should say, is this okay, everyone? Rate of change, all of you, change of velocity, rate of change of velocity, acceleration, right? Rate of change of velocity, rate of change of momentum will be equal to force. Yeah, so over here what they are trying to say, have a look. They are trying to say, okay, how much quickly, the momentum is changing, that matters a lot. Why so? If the change is pretty much quick, right? lesser time. No, I am moving from momentum, let us say like 2 to 5, right? And this 2 to 5 is taking place in 0.001 seconds, right? So the impact of or the force will be more. Yeah, so yes, over here my force not only depends upon change of momentum but rate of change of momentum. Okay, so yes, here the time the rate matters a lot, force will be there, but quicker change, less time taking change, more force. Okay, over here if I will tell you kids that okay, what it is trying to imply, see, let's see over here only. Rate of change of momentum, momentum final minus momentum initial upon time, okay, is equals to force. Similar way over here you can say that yes, you can take up this scenario as mv minus mu upon t is the force. Another formula that you will see. Everyone clear? Okay, yes, here in your second law it is stating us rate of change of momentum, how quickly the change is taking place, right? In acceleration we talked about that or similar way. Okay, so when we say that okay, there is one formula that you will see, F is equals to ma. How this came into picture? This came into picture from this Newton's second law only. Have a look. This only gave us the method. Okay, what does the second law tell you? Rate of change of momentum by time. Yeah, so if I will tell you that this is my mass m of the body moving with velocity u, now in time t the velocity changing out to be v. Okay, initial momentum will be mu, final momentum will be mv. Change in momentum, final minus initial by time. Okay, in place of momentum can I write down mu, mv, yeah, mv minus mu by time, nothing but force. Okay, moreover over here m is equals to v minus u upon t. V minus u upon t, everyone. Yes, acceleration force is nothing but mass into acceleration. Now over here some kids will tell me that okay ma'am, momentum you talked about, right? And over here it's stated directly proportional. So force is directly proportional to rate of change of momentum by time. In order to change the directly proportional, you can introduce a coefficient and keep this coefficient as 1. Okay, and then move on to this step. I skipped it just to give you a small scenario. Yeah, you want, you can. Right? Have a look, everyone. Okay, pretty much simple. Second law is only telling us F is equals to ma. This we use, right? Mass, M for mass, A for acceleration. How it came into picture. This is how it came into picture. Okay, so yes, the quantitative purposes that we use the second law for. Alright, rate of change of momentum, right? That will certainly give me force. Now in this case only I will tell you that okay, when we are jumping from a building, don't do that. I'm telling you, somebody or a book is jumping on the building or anything. Yeah, or if we don't do that, everyone. Yeah, don't try anything like that. I'm just stating. So when people at times fall from a building, they die, right? How they are dying? Because of the speed, because of the momentum, over there, because of that they are dying, because over there, let me show you also. Okay, let me show you here. Okay, now have a look over here. I'm erasing this whole thing, yeah, because you have seen this there only. So when a person is there from a building, yeah, and he is probably jumping, okay, so as he will go down, what will happen? Its velocity will increase. Yeah, certainly you can say, ma'am, if its velocity is increasing, ma'am, momentum will also increase. So, as momentum is increasing, right? So, ma'am, we can certainly say as momentum is increasing, yes, over there, force will be more. Yeah, over there, everyone, force is more, right? But in this particular case, when we talk about forces, rate of change of momentum by time, yeah. So, in this particular scenario, velocity is increasing, but when this boy, this person is coming and hitting on the ground, no, yeah, its velocity, yeah, or the time change or the rate, yeah, the time is very, very quickly changing. Okay, so over here you can see that okay, it is coming and hitting on the ground, and its velocity, no, it is becoming zero very quickly. Yeah, like in 0.001 seconds. As the time is very, very less over here, yeah, as its momentum change is taking place and in very, 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 very less amount of time, so the force acted on it is more. This is why a person dies. Everyone, if the ball is coming towards you, you're going to catch the ball like this. Huh? What will happen? The force over there, right? Of course, you are not giving any time for the momentum to change. Right? And you're not increasing the time. As you're decreasing the time in a very, very less amount of time, yes, the force will be so much that your hand is going to break, your hand bone is going to break, your wrist bone is going to break. Okay, that is why you probably would have seen the, in the matches also, what happens, the cricketer, he or the catcher, right, he's going to catch the ball by keeping his hands, okay, taking back. Why? As he's going to take the hand back, he's going to increase the time. By increasing the time, the force will decrease. Okay, rate of change of momentum matters, but yes, the rate over here matters a lot. Okay, everyone, now moving ahead. So, as we are through with the second law, let's talk about the third law. Very, very easy. Yeah, whatever we do comes back to a certainly action reaction. So whatever you do will occur certainly and come back to you. We usually say that okay, the law of karma, right? Yeah, but in karma, right, the karma arises after a point of time or at times suddenly, but over here everything will occur at that moment of time. There won't be any delay. Yeah, as there is no delay, no, as there is the things happening at that moment of time, right? So yes, the things are out to be, or they tend to be pretty much obvious and clear. Okay, so Newton's third law: whenever one body exerts force on another body, the second body exerts an equal and opposite amount of force. So take up an example. A boy is there, he is applying force on the wall. Yeah, so the wall will also apply force on the boy. Okay, so this is what is action reaction. So when you talk about action reaction pair I am saying, if in this whole universe nobody is there, despite of you, no earth, no any other planet, nothing, empty, and you are there, then Newton's third law cannot occur. You won't feel anything. There should be two bodies interacting, action reaction pair. Yeah, you are going to apply action on another body, another body is going to apply reaction on you. So yes, action reaction pair. Boy applying force on the wall, wall applying force on the boy. Okay, so yes, you cannot apply action onto you, right? So yes, there should be some other body. Right? So what is happening in action reaction? We say the force exerted by the first body on the second. Yeah, and that is action. When the first body will apply the force on the second one, that is action. Moreover, exerted by the second body on the first, okay, that will be your reaction. Right? Now, as we talk about action reaction, certainly we need to be sure about few things. First thing is that there should be two bodies. Second thing should be that okay, the forces they should be of the same nature. Okay, third one will be that yes, there is no delay. And the fourth one will be that yes, the forces are collinear. Okay, now all these points we are going to understand. Before that, let us take up few examples as well. Okay, and then we are going to understand. See, when we are walking, yeah, as you are walking, no, so you are applying force on the ground, right? So that will be considered as action. Now what will happen? I am applying force on the ground. The ground is going to apply reaction onto me. So yes, the force on the foot that my ground will apply, that will be nothing but reaction. Okay, when gun is there, no, where you are shooting the gun, what will happen? The bullet will apply force. Yeah, and certainly the bullet is going to apply the action, right? Of course, you are going to get a jerk. Yeah, so over there you can see the recoil taking place. That is nothing but the reaction. Okay, moving forward and the backward one. Right, similar way when you are swimming also, so what will happen? Push of the swimmer on water. Have a look, action. Okay, push of water on the swimmer, that is reaction. Yeah, you probably would have seen the firemen, right? What will happen? Of course, they tend to hold the water hose, but yes, it is going to move back. Why so? Because of the reaction. Yeah, water particles, they tend to move out with the force, and of course what will happen? Yes, they are the water hose, right? It is going to have the reaction of the same. Okay, moving backwards. Okay, and equal amount. So you can certainly say action, reaction, equal amount, but in the opposite direction. So that is why we mention it like it. Okay, now as I told you that the forces, they should be of equal nature. Yeah, equal amount, equal nature, no delay should be there. Moreover, if I say these are the two bodies, okay, let me use some other color. Yeah, mass 1 and this one would be mass 2. Okay, so what will happen? Of course, like this you are going to see action, reaction. Okay, let me make it 1, 4, 7, 2. Okay, so here you can certainly see that, okay, action with reaction. So yes, of course, over here also don't get confused that, okay, if you will see, no, this if you will see in place of F1, right, you can see that, okay, if it is written 2, 1, so force on 2 due to 1. Yeah, force on 2 due to 1, so, and it will be force on 1 due to 2. Okay, right, action reaction pair. Moreover, no delay, that means then and there the thing will occur. Yeah, collinear, they will be in the same line. Moreover, of the same nature. Why so of the same nature? So if I will give you that, okay, there is a box kept on a table. Yeah, there is a box kept on a table and on earth. Right, so what will happen? Of course, the earth, right, will try to attract it. Right, moreover, the table will apply a normal force. Over here, can you say that, okay, these are the action reaction pair? No. Why so? Because when the earth is pulling the box, of course the box will also apply force on the earth. Yeah, this is going to be action reaction pair, so they should be of the same nature. Normal with normal, gravitation force is gravitation force, magnetic force is magnetic force. Yeah, they should not be in contact with each other. That is not the scenario. They should be of the same nature. Okay, earth attracting box, box attracting earth, that. Yeah, both of the same nature. Okay, moreover in the same line, no delay taking place over here. And yes, when you say no normal and this force over there, the earth is attracting the box, right? These are not action reaction pair, these are action reaction pair. Okay, then and there the thing will be occurring, same nature, very very important, and acting on the, see, acting on other body, not on yourself, right? So yes, the force will act on another body. Yeah, action occurring, reaction occurring, right? Have a look over here, no? So swimmer pushing the water, water pushing the swimmer. Okay, swimmer on water, water on swimmer. Okay, same nature. Yeah, pretty much clear with action reaction pair. Okay, so over here, yes, we generally see an encounter these action reaction pair and the Newton's second law of motion that we talk about. Okay, that whatever thing is happening, whatever you do, so shall you reap. Yeah, similar scenario over here also. Okay, and yes, they will occur and act in pair. Now let's talk about the last thing. Okay, I'm not going into brief of that, yeah, because this topic is probably taken out from the CBSE board, yet I'm giving a small hint onto it. Conservation of momentum. See, when we talk about conservation of momentum, we generally say, I believe momentum is pretty much clear. Okay, when two or more bodies act on another, their total momentum remains constant. Okay, so we say whatever thing is happening before they are interacting, after they are interacting, their total momentum will remain constant. Also, this is called as the law of conservation of momentum. That means whenever one body gains some momentum in a system, the other will lose in order to maintain the constant. Yeah, total is 5. One is getting 3, one is getting 2. Then another one is getting 3, the other one is getting 2. So gain and loss need to be maintained. One will gain momentum, some other one will lose the momentum. But yes, this law states as momentum can never be created nor be destroyed. So if I tell you, have a look over here. Yeah, before collision, the momentum, the total momentum of body M1, U1, M2, U2, this was the total momentum before collision. Okay, after the bodies are colliding, yeah, the momentum will be M1, V1, M2, V2, and the total will remain same. Okay, so before collision, after collision, so yes, the total momentum before the collision will be equal to total momentum after collision. Whatever changes are taking place, right, they are going to, one will gain, one will lose, that will be counted apart. Okay, everyone, right, this is the last thing, that is conservation of momentum. Right, momentum need to be conserved. This thing we generally encounter when there are gas particles there in a balloon. They are going to collide with each other. Yeah, some particle is going to gain momentum, some is going to lose momentum, colliding. Yeah, but the system remains constant. The total momentum remains constant. Okay, there is no destroying or creation taking place over there. Okay, so I believe till here the things are clear. All of you do share your views and the answers there in the chat. Thank you so much, everyone. Keep on practicing and keep on revising. Thank you so much all.